Let's talk about something we all do, probably every single day. Check the temperature. It feels so simple, right? But the story of how we got to a point where we can put a precise number on hot and cold is actually incredible. It's a journey from just a human feeling all the way to a fundamental constant of the universe. Let's dive in.
And I mean, just think about it for a second. What's the first thing you check in the morning? Probably the time. And what's next? For a lot of us, it's the weather, right? The temperature. Every time you do that, you're tapping into a scientific quest that's been going on for centuries. The National Institute of Standards and Technology puts it perfectly. After time, temperature is pretty much the thing we measure most. But, it wasn't always that simple.
And that was the real problem, the core of it all. For most of human history, hot and cold were just feelings, sensations. There was no way to quantify them, no way to prove that the water in one bucket was exactly as warm as the water in another. So how on earth did we get from a subjective feeling to a precise, reliable number?
So here's how we're going to break it down. First, we'll look at a world without numbers, where you can only see temperature change. Then, we'll get to the revolutionary idea of actually putting a number on it. After that, we'll join the hunt for the coldest possible temperature, absolute zero. And finally, we'll see how electricity just completely changed the game. Okay, so let's go way, way back. I want you to imagine a time with no forecast, no thermostats. A time when you couldn't measure hot or cold, you could really only watch what it did to the world around you. So you had these early pioneers, folks like Hero of Alexandria, and later, the one and only Galileo Galilei. They created these amazing gadgets called thermoscopes. And the idea behind them was actually pretty simple but really clever. They all worked by watching a substance, usually air or colored water, expand when it got hot and shrink when it got cold. You could literally see the liquid level in a tube go up and down, showing you, hey, it's getting warmer, or, oh, it's getting cooler.
But here's the catch. These things could show you that a change was happening, but they couldn't give you a number. There was no scale. So what you called a little warmer in your workshop had absolutely no connection to what someone else called a little warmer in their lab across town. They made this invisible thing visible, but they couldn't make it comparable.
And solving that problem, how to make temperature comparable, is what led to the next huge breakthrough.
This is what gave us the modern thermometer, the invention of the scale. And this is where things get really clever. The big idea was, instead of just relying on some random instrument, why not anchor the measurement to something that happens the exact same way, every time, everywhere on Earth? So scientists turned to nature itself for fixed points. Things like the exact temperature water freezes, the exact temperature it boils. These became the universal signposts for everyone to use.
And that idea was the key. In the early 1700s, people like Daniel Gabriel Fahrenheit and Andreas Celsius used these fixed points to create the first standardized, repeatable scales. For the very first time in history, a reading of, say, 10 degrees could mean the exact same thing in London as it did in Paris. The feeling finally had a number.
But of course, as soon as you put a number on something, scientists start asking even deeper questions. If the number can go up, how far can it go down? Is there a bottom? Is there a final, ultimate limit to cold? Well, to answer that, we had to totally rethink what temperature even is. It turns out it's not just a number on a thermometer. It's a measure of energy. It's a measure of the actual motion of the atoms and molecules that make up literally everything. All that jiggling and vibrating on a microscopic level, that's heat. Basically, heat is motion. Okay, so if heat is motion, then making something colder just means you're slowing those molecules down. Which leads to this incredible thought experiment. What happens if you could keep cooling something, slowing them down more and more and more, until all that microscopic motion just stops? Well, back in 1848, a physicist named William Thomson, you might know him better as Lord Kelvin, he actually did the math. He calculated the answer. And he predicted that the absolute bottom, the point of zero motion, was negative 273.15 degrees Celsius. He called it absolute zero.
And this is a really huge idea. Absolute zero isn't just really, really cold. It is the fundamental floor of the universe. It's the point where particles have the absolute minimum energy they can possibly have. You literally cannot get any colder because there's no more motion left to remove.
And that's why the Kelvin scale is such a big deal for scientists. You see, the Celsius scale is super useful for us, but its 0 point, the freezing point of water, is kind of arbitrary from a cosmic perspective. The Kelvin scale, on the other hand, starts at the real bottom. 0 Kelvin is absolute zero.
It's a scale based on a fundamental limit of the universe, which is why there are no negative numbers in Kelvin. You can't have less than zero motion. For scientists, this makes all kinds of calculations about energy and gases way more straightforward.
So for centuries, the story of temperature was all about thermodynamics, about things expanding and contracting. But then, in the 19th century, an accident in a completely different field of science changed everything.
Okay, so just remember, up to this point, pretty much every thermometer ever made, from Galileo's little glass tube to the most precise mercury ones, all worked on one simple principle. Stuff gets bigger when it gets hotter. It was a purely mechanical process.
But then, in 1821, this physicist, Thomas Johann Seebeck, is messing around with electricity and magnetism. He takes two wires made of different metals, joins them in a loop, and, well, he wasn't trying to make a thermometer, but he noticed something really bizarre. When he heated up one of the spots where the wires were joined, an electrical current started flowing through the loop. What he'd stumbled upon was a direct link between a temperature difference and electricity.
And this, of course, got named the Seebeck effect. Now, what made this so revolutionary was that the amount of voltage it produced was directly proportional to the temperature. This discovery is literally the principle behind the modern thermocouple, which is one of the most important and widely used temperature sensors in all of science and industry today.
I mean, this was a complete game changer. Suddenly, measuring temperature wasn't just about watching materials expand anymore. It was now fundamentally tied to electromagnetism. This discovery blew the doors wide open for every digital thermometer, electronic sensor, and automated system we depend on today.
So, think about it. We started this whole journey just trying to put a number on a simple feeling. That quest led us to understand the motion of atoms, to discover the absolute limits of cold, and even to find hidden connections between the fundamental forces of nature. We went from a simple glass tube to sensors that can measure the heat of a distant star or the chill inside a quantum computer. Which really just leaves us with one big question: what new frontiers will we need to measure tomorrow?